In our previous classes, we discussed about the solubility of solids in liquids, wherein the solubility and related properties we explained in terms of the Raoult's law. And then also we discussed about solubility of liquids in liquids. That is what we discussed in terms of ideal and non-ideal solutions and the corresponding properties. Now, in this class, we discuss about solubility of gases in liquids, the principle governing the solubility of gases in liquids, factors affecting the solubility of gases in liquids is what we discuss. When it comes to solubility of gases in liquids, equation wise we can represent it as gas, that is a solute in liquid, will form gas liquid solution. Gas liquid solution. Characteristics of a gas liquid solutions and what are the factors that will affect the solubility of a gas in liquid. First of all, whether the gas is soluble in liquid or not, how do we know? The very simple thing is that aquatic species like fish is present in water bodies, lakes, rivers, sea, etc. And the aquatic fish gets oxygen. Where from it gets oxygen? Obviously, that oxygen is nothing but the one that is present in, that is dissolved in water of that water body. So, that is a clear example of existence of gases in liquids, that is nothing but solubility of gases in liquids. And another common example that all of us know is that aerated drinks, that is like in aerated drinks, carbon dioxide is dissolved in water. So, is the reason that when we open up a bottle, a gas is evolved, that is carbon dioxide. So, these are all certain examples of solubility of gases in liquids, right. Now, this dissolution of gas in a liquid is first of all is an exothermic process. When it comes to the factors that affect the solubility of gases in liquids, the very first thing is nature of gas and liquid, that is solute and solvent. As you know, like dissolves like, in the case of solids and liquids, already that what we know. Here again same principle is applicable. If you take the example of oxygen in liquid water, the solubility, it is very less. The reason being that oxygen is a non-polar covalent molecule, water is a polar solvent, non-polar gas very difficult for it to dissolve in polar solvent like water. So, solubility of oxygen in water is very, very less. And so, it is this basic principle of like dissolves like. In lower classes you must have learned that like dissolves like. Therefore, oxygen being non-polar, it is less soluble in water, less soluble in water. HCl is more soluble in water, because HCl gas in water dissolves completely as you will get the ions. Carbon dioxide is also of course non-polar, but dissolves, because the carbon dioxide will react with water. So, this is polar, oxygen non-polar, carbon dioxide non-polar, but soluble, because it has polar bonds and reacts with water. Oxygen being non-polar and non-reactive, it is less soluble. HCl being polar and dissociate into ions, will dissolve very high. Carbon dioxide, it is non-polar, but the bond CO bond is polar and it will dissociate into ions. So, this is also soluble. So, polar covalent molecules, gases are less soluble in water. Non-polar gases like HCl, ammonia are more soluble in water. Again, non-polar is more soluble in non-polar, and if you take HCl, HCl is very less soluble in benzene, because HCl is polar, benzene is non-polar. So, this principle of nature of liquid and nature of gas, if they both are of similar nature, they are more soluble in in one another. The polar gas is soluble in polar solvent, non-polar gas is more soluble in non-polar solvent. Either we can say it is polar and non-polar nature, or the other way is reactivity. If the gas is able to react with the solvent, then again we say that it is more soluble. For example, carbon dioxide in aqueous solution of potassium hydroxide also dissolves, because carbon dioxide is absorbed by KOH to form the K2CO3. Okay. So, like this, solubility of a gas in liquid solvent depends on the nature, polar and non-polar, and its reactivity with the solvent, right. The next what we discuss is the effect of temperature and effect of pressure on the solubility. Now, when it comes to the effect of temperature, as a process is, as the dissolution process is exothermic, as the dissolution process is exothermic, increase in temperature will not favor the solubility, because according to Le Chatelier principle, exothermic reactions are more favored at lower temperatures. Exothermic process is favored at low temperature. So, here as the process being exothermic, low temperature favors the solubility. And in fact, this is the reason that one of the very bad effects of warming, global warming, the very bad effects of global warming is the decrease in population of aquatic environment, aquatic animals. The reason being that with increase in temperature, what happens? Solubility of oxygen in water decreases. As a solubility being exothermic, the solubility of oxygen in water decreases with increase in temperature. Due to global warming, temperature increases. Due to increase in temperature, solubility of oxygen decreases. As the solubility of oxygen in water decreases, availability of oxygen to the aquatic environment, to aquatic animals like fish decreases. So, the fish are due to the insufficient oxygen, due to the non availability of oxygen, fish like aquatic animals population is getting decreased, or they will die. So, that is one of the simple application by which we can say that we can understand and we know that with increase in temperature, solubility of oxygen in water or solubility of a gas in solvent like water decreases. And the third is effect of pressure. When it comes to effect of pressure, once again, as you can see it over here, that this is gas, as the gas gets dissolved in a liquid solvent, its volume decreases. So, the other way around, what you can understand is number of moles of gas. Here you are having the pure gas, but here this is gas in solution. So, number of moles of gas is decreasing or the volume is decreasing, and at constant pressure N is proportional to V, right. So, volume is getting decreased or number of moles of gas is decreasing. Now, increase according to again Le Chatelier principle, increase in pressure favors decrease in number of moles of gas or gas volume. Therefore, increase in pressure increases solubility of gas in liquid. More the pressure, more is the dissolution. As you keep on increasing the pressure, as even that we know very well, suppose if you have a vessel in which water is taken and if you have a certain gas to dissolve, if you keep on increasing the pressure with the help of a piston, external pressure, then that means you are pushing more and more of gas towards the liquid and more gas will get dissolved, right. So, this is what from the Le Chatelier principle technically we say that as the number of moles of the gas is getting decreased or the volume of the gas is getting decreased, therefore, increase in pressure will favor the forward reaction, that is the dissolution of the gas. Now, this effect of pressure and the solubility, or in other words the amount of gas that dissolves with pressure, the effect of pressure and the amount of gas dissolved, or the amount of gas dissolved as and its corresponding pressure, these two are related by Henry's law. Henry's law is given to explain the effect of pressure on dissolution of gases, the amount of gas dissolved, or the amount of gas dissolved to pressure, pressure to amount of gas dissolved. That relation, numerical relation, is what we will discuss in the Henry's law. So, the other way Henry's law is nothing but which explains the amount of gas dissolved in a solvent at a given particular pressure, and so it is nothing but the relation of pressure and the amount of gas dissolved. This is what we discuss in the Henry's law, right. Henry's law. This Henry's law, as I told, it relates the amount of gas dissolved in a given solvent to form a solution with respect to the pressure exerted by the gas on the surface of the liquid. And on the other way around, it gives the relation that at a given pressure, what is the amount of gas dissolved. That relation we can get it from Henry's law. Or now, according to Henry's law, one statement is the amount of gas dissolved in a solution is directly proportional to the pressure it exerts on the surface of a liquid. Means if the amount of gas is say A grams, then what it says is A is proportional to P. A is the amount of gas, P is the pressure. And this A is then is given as K into P, where K is called Henry's constant. But the other way also the statement is given according to which pressure exerted by a gas on the surface of a liquid in a solution is directly proportional to mole fraction of gas in the liquid. Mole fraction of gas in the liquid. That means pressure exerted by the gas, that is P gas, is directly proportional to mole fraction of gas in the solution. This implies P is equal to Kh into mole fraction. P is equal, here if you look at it, A is equal to K into P, K is what we call Henry's constant. Here P is equal to Kh into X, where this Kh is Henry's constant. Now actually this is the Henry's constant now what we use for different gases. This constant is inverse of this constant, as you can see from the two equations. One should not get confused. Now the Henry's constant what is given for gases, as you can see here, that each gas will have its own Henry's constant. This Kh, the other way can be defined as Kh is nothing but pressure exerted by a gas and the mole fraction of the gas is 1, right. So each gas will have its own Henry's constant depending on its nature of the gas, right. So this Kh is Henry's constant, which is characteristic of the gas. For different gases we will have different solubility. Now here from this relation what you can understand is this Kh is at constant pressure, Kh is inversely proportional to mole fraction. So the meaning is that the or 1 by x is inversely proportional to Kh. So the meaning is that a gas with higher value of Kh is less soluble, gas with lower value of Kh is more soluble. This is now we will elaborate. So this Henry's law explains the solubility of gases in liquid solutions. The more appropriate way is of this is more significant, as here it is given in terms of the weight. This statement and this relation or this constant practically we do not use. The one that what we use is this statement, according to which that pressure exerted by a gas in a solution is directly proportional to mole fraction of the gas in that given solution. Kh is Henry's constant, which is characteristic of each gas. Different gases will have different Henry's constant values. So, here as we told that pressure exerted by gas is directly proportional to mole fraction of gas, or P gas is equal to Kh into X gas. So, X gas is proportional to Kh. So, from this, higher the value of Kh of a gas, lower is its solubility. Gases which are easily liquefiable, gases which are easily liquefiable, this is a very important statement. Gases which are easily liquefiable means having lower critical temperature or more soluble, because easily liquefiable gas means that gas easily will miscible with water, two liquids, it will become like two liquids. Gas which is easily liquefiable means it will become like miscibility of two liquids. So, gas which is more easily liquefiable like carbon dioxide, ammonia, they are more easily soluble. But if you take gases like nitrogen and oxygen, helium, not soluble at all, so are more soluble, and their Kh is also less. Gases like helium, neon are the gases with high value of Kh and least soluble. Gases like nitrogen and oxygen also highest, these are high, less soluble. Gases like ammonia, carbon dioxide, sulfur dioxide, sulfur trioxide, so on and so forth, their Kh values low Kh value and more soluble. In fact, this is the reason that deep sea divers will carry cylinders of oxygen also mixed with helium. The reason being that nitrogen and helium, if you look at it, solubility of nitrogen is relatively more in water than helium, as I told you here. So, as it more soluble, there is a possibility that divers will inhale more oxygen than required. To prevent that, helium is mixed in that instead of nitrogen. The helium content is increased and the mole fraction of nitrogen is lowered. As a result, what happens is the dissolution decreases and the available oxygen for the divers will be sufficient enough when appropriate proportion of helium is mixed in that. This is a very simple application of this. And even in oxygen and nitrogen mixture in the lungs, it is the oxygen is more soluble, and as it dissolves oxygen in the lungs and it is carried out throughout the body as oxygen is dissolved in the hemoglobin and it is carried forward, it is carried out the entire body. So, that is because of the solubility of oxygen in water. So, like this we have daily uses, applications of solubility of gases in liquids. And practically, as all of you know, that when you open a cold beverage bottle, aerated drinks, lot of gases evolved. What is the reason that gases evolved? Because the gas that is carbon dioxide in bottle is made to dissolve more amount. When it is possible for more carbon dioxide to dissolve, when the pressure is increased more. When the pressure is increased more gas is dissolved, and then at high pressure it is sealed. So, as soon as you open it, the pressure will reverse it. That is the reason we get sudden burst of gas as you open the beverage bottle. That is because of the Henry's law, that higher the pressure, more is the solubility. Higher the pressure, more is the solubility. So, at very high pressure the gas is made to dissolve. So, when you open it up, the pressure releases and gas evolves. That is the reason we find carbon dioxide coming out as soon as we open the beverage bottle, right. So, these are all the various applications of Henry's law that in our daily life that we come across. So, this in totality gives us the picture about solubility of solids in liquids, which we discussed in terms of the vapor pressure, solubility of liquid in liquid, again we discussed in terms of vapor pressure, and of course, the corresponding properties of colligative properties for both of them, and then of course, the solubility of gases in liquids. So, it is all soluble. The entire liquid solution means solid in liquid, liquid in liquid, gas in liquid. All the three is what we discussed. Still we have some other additional topics like fractional distillation curves. These are some applicative part is still we have to discuss, right. Fractional distillation of liquid solutions. This is, first of all, distillation means when we have two liquids in a mixture, then first of all distillation, a liquid is converted into its vapor. That vapor, when it is condensed back to a liquid to vapor, this is evaporation. This is condensation. This whole process is what we call distillation. This is what we call distillation. As you know, natural distillation process is nothing but rainwater, where water from the river body, water body, river, lake or anything will evaporate first, reaches to higher atmosphere, and the clouds will get added up. When sufficient pressure is obtained, it will condense back into liquid state. So, this process altogether, evaporation followed by condensation, is what we call distillation. Using this distillation process, useful to separate two liquids from a mixture, that is liquid solution. How it is useful? Because suppose if you have two liquids A and B, which are having boiling point TA, TB. Suppose TA is less than TB, boiling point of liquid A is less than boiling point of liquid B, then the one with lower boiling point evaporates first. So, this will be in vapor phase, and this will be left in liquid state. So, A will become more in vapor phase, B will become more in liquid phase. The meaning is composition of A will be increased in vapor phase, composition of B gets increased in liquid state. So, when you do a continuous process of evaporation, then after some certain time, when vapors are condensed back, in those second, that means suppose from one vessel, here the vapor is allowed, and of course, this is cooled and this is collected here, this is here it is condensation and here it is evaporation. Initially you have started with A and B. When you started with A and B, here this XA is the mole fraction of A and XB is the mole fraction of B. As the temperature is increased, what happens is that here you will get more A, the vapors, the vapor will have more A, and now this is Ya and Yb, and this is collected over here. Here again you will get a mixture of A and B, but here the mole fraction is Ya and Yb, and in this Ya, if Ta is less than Tb, then Ya is greater than Yb, and then remaining X dash A and X dash B, if you take, then this is X dash A is less than X dash B. This further if you do again repeat, then here again you will get A plus B. Now it is Za and Zb. Your Za still greater than Zb, also that Za greater than Ya greater than Xa. So, that means when you come to the third stage, the fraction of A in the solution is increased further. So, suppose if you start with say 10% of that is 0.1 mole fraction of A, then by the time you come here it may be 0.5, and after it is coming over here it may be 0.9. So, that you are able to increase the fraction of A in the third stage. So, and if you keep on doing it repeatedly, the last fraction that what you collect will be richest in A, or you may have only liquid A, right. So, when you repeat it n number of times, then the last fraction that you collect after sequential distillation process, this is what we call fractional distillation. First distillation is carried out, then certain fraction is collected, this fraction is again condensed and again distillation, again you will get another fraction, that fraction is again distilled. So, like that you are keep on doing the distillation in different fractions, so that the last fraction obtained will be richest in more volatile liquid. Okay. So, this fractional distillation now is in brief is nothing but a separation technique useful to separate mixture of two liquids based on the difference in their boiling points. Lower the liquid with lower boiling point will evaporate first, and the fraction collected will be richer in the more volatile liquid, and the residual left, the residual liquid that is over here, the residual liquid will be richer in less volatile liquid. That means the one with the lower, the one with the higher boiling point, right. So, like this is what is a fractional distillation. Now, here what we are going to discuss is, suppose after one distillation if you collect certain fraction, you started with Xa and Xb as the mole fractions of the two liquids A and B. When you started with the two fractions, the mole fractions of the liquid as Xa and Xb, and if distillation is carried out, then here you are collecting certain fraction. In this fraction, the mole fraction of A and B is Y and YB. If XA and XB are given, how to calculate YA and YB and how to calculate ZA and ZB, so that for a required purity of the liquid, how many such steps of fractional distillation is to be carried out, that also we can calculate. And also if you draw a graph for the variation in the mole fractions of the two substances A and B in both liquid phase and vapor phase, a particular composition of a liquid starts boiling at what temperature, also we can find out. So, that graphs that are drawn at for the different fractions versus the temperature is nothing but fractional distillation curves, which we are going to discuss now. Distillation is a process in which a liquid is evaporated first, then the vapors are condensed back into liquid. So, it is a process involving evaporation followed by condensation, and the natural example of this distillation is the way we get the rain.